Okay, so I'm going to present a paper that was presented at Usenix ATC in 2018. So these are exactly the same slides. I just updated one of them. You'll see where it's been updated. Maybe I'll mention when some of the numbers are out of date. My work is on Coccinelle, 10 years of automated evolution in the Linux kernel. So basically this is reporting on a tool that was developed around 2004, 2005, became publicly available in 2008. And so this is our kind of retrospective on what have we done for the last 10 years, what went well, what should we have thought about better, and so on. Okay, so the context of our work is the Linux kernel. Linux kernel is an open source operating system. It's used basically everywhere: smartphones, battleships, stock markets, supercomputers. This is a number that's been updated. Today it is 18 million lines of code, and it's still growing. And it has to change a lot often. We find bugs. I'm sure you've heard of Meltdown and Spectre. So those bugs caused huge changes all the way across the kernel. And different performance issues that are found, new kinds of hardware that appear, and so on. All of these things have an impact on the kernel, and the impact can be pervasive, or it can cover a particular subsystem, such as networking, and so on. But at this code size, everything you do is quite big. So basically, in terms of maintenance, we have some issues. How can we perform evolutions in such a large code base? So anytime you want to do something, you may feel frustrated by the fact that you're going to have to do it 500 times. It seemed okay when you had to do it only 3 times, but 500 is kind of might discourage you from actually doing the work. And another issue is bugs. So in 18 million lines of code, sort of experience shows that whenever you have made a bug once, you've probably made that bug maybe 3 or 4 other times. Surely in such a large code space, you could turn up 3 or 4 other times. So how are you going to find those 3 or 4 other times in 18 million lines of code? So we're thinking about this problem. How can we better maintain such a large code base? And in thinking about that, we thought about how do Linux developers already maintain their code, which is that they think about patches. They create patches, they make changes, and then they use diff to find out what the patch is. And then they send the patch off to a maintainer who's going to look at the patch. That person will, or several people actually will look at it and say, it seems good, it seems not so good. Maybe you should change this. People are used to looking at things that look like this. So basically what we have is we have an extract of code, and we have some lines that we don't like. They have little minuses in front of them. They have some lines we want to put in their place. They have little pluses in front of them. And, well, that's kind of about it. Usually these are accompanied by some kind of helpful message that's going to explain to you what's going on. But basically, the developers are familiar with actually looking at the code and seeing what's going on. So we thought about that as a way that we could use to somehow help automate this or make this maintenance more robust in the future. So we had a simple idea, which was to take these patches that look like this and make them somehow more abstract. So this patches are a very nice thing. It's a completely automatic, not completely deterministic way of applying a change to some code. As long as you happen to have exactly the same code as this, we can make exactly this change, and it's like transportable from one place to another. But there's this problem about you have to have exactly the same code as this. So it's not going to be very useful if we want to do some kind of general purpose evolution. We're interested in perhaps doing our evolution. If you notice the change here is we turn an M into a Z. So we might be interested in changing many M's to Z's across the code base. But they're not necessarily going to have exactly this code nearby. And they're certainly not necessarily going to be in lines 1,348 and so on. So we want to take this thing, its advantages, and make it just a little bit more abstract, and so that we can have something that's much more reusable. So this is our solution. So basically, we've kept the idea, we've kept little @ signs. We've kept the idea of fragments of code that are removed and fragments of code that are added. We have changed the line numbers, which were not very useful in our situation. We've changed them to a declaration of some metavariables. So this is how things become more abstract. Instead of having the argument to kmalloc be whatever it was before, size of struct Zoran FH, which is going to be particular to a particular file in Linux kernel. We will just let it be any expression E1, any expression E2, and the result is going to be stored in any expression X. Okay, but it's not just any expression. Actually, if you look at this more closely, we have X here and we have X here. So the value that's returned from kmalloc ought to be fed into a memset. Here we have something concrete. The first argument, second argument of memset should be a 0. Basically, the idea is we're allocating some memory and we're zeroing it. And so there was the idea that we could save a little code space by turning this combination of functions into just one function. So that's what we're trying to do. So we see these different relationships in different places. Again, also the size of the allocation should be the same as the size of the memset. And so if we have these properties, that is in this code that we're trying to match, and then that we're trying to remove, then we would like to replace that code by this call here. Are there any questions? Because this is like the whole idea of the talk. So, yes. Thank you.
You're saying this. What can be about the semantic differences? For example, if I just change one line of a two-line if in some condition, and that if basically removes the first version of the first part of this and adds a new kind of variable, new condition, how I can interpret that change in the terms of your semantic patch language?
Okay, so I'm not completely sure to understand the question. Maybe the answer to the question is that, I mean, we say semantic patches, they're not that semantic. It's very much tied to specific fragments of code. So what you can do is you can abstract over some sub-expressions. We have this ... operator. And the ... operator, it's meant to be kind of an intuitive, you're writing on a napkin and you tell your friend you should do your change like this, and we don't really care about what's going on in here. But there's a bit more to it than that, which is that it's actually moving all over all possible control flow paths. And so we're checking that this kmalloc is actually always followed by the memset. But it's not we're not doing things like, we don't know anything about aliases, we don't know anything about data flow, and things like that. So it doesn't have that aspect of the semantics built in.
Okay.
Is that clear enough?
Yeah.
Okay, thank you. Yes?
But yeah, I mean, that sort of would have been my question as well. This is not, this still looks very syntactic, right? So patch, a classic patch is purely syntactic.
Mm-hmm.
This still looks very syntactic. It just looks like a parameterized patch, but actually it knows something of the underlying language semantics. You were talking about control flow just now, so it can't apply, say, where that memset is in a different function, and therefore the variable x happens to have the same name, but is a different variable, that then it wouldn't apply. Is that correct?
So the question is, for example, this ... maybe how far does it go? So everything actually is intra-procedural, and so the memset has to be in the same function. The Linux kernel, I mean, we really made this tool for the Linux kernel. Linux kernel tends to have quite big functions, and so having this restriction has not been a big problem in practice. Usually, these kinds of patterns are going to be inside the same function. It might not work as well in some other software. It's not what we're targeting. Is it clear enough now? So the language, we have a language, it's called the semantic patch language. We have a tool which is called Coccinelle. Using the semantic patch language, you write things like this. You can write multiple rules. They can have dependencies on each other. And then Coccinelle will take these rules and it will apply it to your entire code base. And as I mentioned before, development began in 2006, and it was first released in 2008. And so here's how people have been using it. So today we have almost, maybe it's 7,800 commits in the Linux kernel that mention Coccinelle. So this is the different breakdown over the years by different kinds of people. These are the developers of Coccinelle. So in the beginning, we kind of used our own tool and maybe tried to show to other people they could be useful for things. Another line that's of interest is the Linux kernel maintainers. So these are the people who have actually worked on the Linux kernel for a long time, who are responsible for different subsystems, maybe networking or something like that. So you can see the use taking off here. There's a big spike here when some people did some really large reorganizations. The spike seemed to be kind of a surprise. But now we see in the last few years the use kind of more taking off. Again, a lot of this is because people decide to do something big, and they realize that to do something big, they need a tool to help them, and they're familiar with the tool, and so they do their big thing with this tool. There's some other maintainers here. These people are interns. They don't have much experience with the Linux kernel, but then they have lots of patches using Coccinelle, so that shows that it can be used by people who don't have that much experience. There's also a whole bunch of these semantic patches which are inside the Linux kernel, so people just say make Cocci check, and then it will check their code, and it will make some changes for them if they've used kmalloc instead of kzalloc. It would also find some bugs. Using this pattern language, you can find bad patterns, and so it will report on maybe you have a double lock or a double free or something like that. And then another thing we counted is the number of developers who have at least one commit that touches 100 files. So this is the idea of like a really big change, a big kind of tree-wide kind of change. And about half of the people who have done that kind of work have been using Coccinelle. So somehow we're reaching the people that we would like to reach. So the question is, how did we get here? So we started as like a tool developed in research group. We were basically 4 people, a couple postdocs, a couple faculty. We had an idea, we implemented our idea, and somehow we got to the point where lots of people use it and it has impact on the Linux kernel, but also actually on other kinds of software. So what I'm going to think about is what we did in terms of various dimensions, what were the choices we made, how we had to evolve those choices over time, somehow to reflect how did we manage to be successful, maybe perhaps despite some wrong choices we made in the beginning. So we'll think about expressivity, performance, correctness guarantees, and dissemination. Okay, so expressivity. So our basic idea was that the Linux kernel developers will find it easy and convenient to describe needed code changes in terms of fragments of removed and added code. So sort of what I'm saying is like everything one would ever need to do in Linux kernel, you can just describe as remove some lines of code and add some other lines of code. Okay, so that's kind of exaggeration. We've already discussed some of the limitations of the approach. So it's kind of an important thing is that we're not actually targeting everything you'd ever want to do in Linux kernel. We're just targeting a certain kind of change that people have to do over and over again, and that in practice has been shown to be kind of error-prone because anytime you let a human start removing lines of code and adding other lines of code, things can go wrong. So this was our basic idea. You just remove stuff, you add stuff. It's good, but maybe you need some more things. So as we made the tool available, people used it. We were confronted with what happens in the real world. There's some features of C that we didn't consider in the beginning, some kinds of meta variables, so allowing people to abstract over more different kinds of things. So that's kind of like C is a really big language, so that's fairly obvious. Over time, we found the need first for abstracting over positions of things. So here we're going from describing explicit patterns of code to somehow giving people access to some properties of those code. So basically a position variable, you can attach it to any token and it will find the position of that token. And then you can reason about the position of that token. A position of this token should be the same as or different than a position of some other token. And then you can combine it with this last approach here, which is adding scripting. And scripting lets you do arbitrary computations, but among those computations, you can actually print out positions. And now you can do bug finding, and you can explain to people that on line 27, they have a double free or something like that. So these two things, it was actually a master's student who wanted to do these things. He wanted to do bug finding, to find buffer overflows and all different kinds of things that Coccinelle is not very good at because Coccinelle doesn't know anything about the values of things. So the idea was the scripting would let him reason about values of things. So that idea actually didn't work out at all. basically what he ended up with was very generic patterns and lots of code to manage the values, the propagation of values, just like you would write in any kind of ordinary compiler, any kind of ordinary, if you use, for example, LLVM and you want to implement some analysis, that's kind of what he ended up with. So that wasn't really in the spirit of what we wanted to do. But letting you do scripting lets you do lots of other interesting things, report bugs, count numbers of things, collect numbers of things. If you want to know what is the set of all the functions used in a certain part of the Linux kernel, then you can find that out. So here's just a simple example. This is a extract of a rule that was written by someone else to go into the Linux kernel to find some kind of issue. Actually, there's a whole bunch of functions here. We don't like those functions anymore, and so we want, whenever somebody commits something, if they want to run, make Coxie check on their commits, then it will complain that they shouldn't be using these functions anymore. So it's quite a simple thing. We're going to match the calls to these functions that we don't like. We record their position here with the @p, @p, who's position p. Here we have some Python code. This rule has a name. It's called R. And now down here in R, we can refer to the object that was used as the argument of the thing, and we can refer to the position, and we can print out a friendly message that will say you shouldn't be using this particular function on this particular line on this particular object. So it kind of gives you a nice trade-off between matching and computing, and it makes everything somehow much more flexible. So if you have new features, it's only interesting to have new features if people actually use them. It's a bit hard to understand how much people use different features of a tool. It's an open source tool. People do whatever they want with it, and they're not necessarily obliged to report to us what they've done. But some commits in the Linux kernel have semantic patches, and so we could look through those commits and see what they say. And some of them use position variables, some of them use scripts. About half of them that use position variables or scripts are from outside of our group, so we made these features and other people seem to be using them. The semantic patches in the Linux kernel all have a mode where they print these kind of warning messages that we saw on the previous screen, and so they obviously use these features. So the next question is performance. So basically, our idea is that the tool should be usable on a typical developer laptop. Okay, some other people have done tools, very precise tools for reasoning about C code, where you had to take your code and then put it out on the cloud and get 100 servers, and then 3 weeks later you would get your results. So that was really not the kind of option that we were aiming for. We're thinking of the typical developer, maybe kernel developers, they kind of work in cafes or on mountains and things like that. They're not necessarily connected to a large server all the time. So our code base in 2007, basically when we were initially working on the project, was 5 million lines of code, 16.5 million lines of code in 2018, 18 million lines of code today. It just gets bigger and bigger. So performance is kind of an important issue. So we made some design choices in the beginning to kind of match the kind of trade-off between performance and the amount of, the kind of problems we were targeting to solve, the kind of degree of accuracy that we thought those problems actually needed. So we're intro procedural, as mentioned in one of the questions. Basically, we just work on one file at a time and one function at a time. So we can have, I haven't shown it, but you can make a bunch of different rules, and the different rules can match in different functions, and then they can collect information in different places, but all of that's going to be in just one file. By default, we only process the .c files. You can also use an option to tell it to process the .h files. Linux kernel developers are pretty well behaved about putting interesting code in the .c files and a bunch of hash-defined declarations in the .h files, and so often it's useful to only process the .c files. A big issue in the case of C is includes and the C preprocessor and all of these things that go together. So this goes together here, includes and macros. So the decision of Coccinelle for various reasons is that first we have our own C parser. We just look at the C code. We try to deal with it as we see it. Okay, so on the one hand, that was very important because we want to do source-to-source transformation, and so you want the code to come out in the end looking as it was in the beginning. Okay, so many other tools for processing C, especially things that are built into compilers, are going to run the C preprocessor first. And so in the source code, you might have a macro call. In the actual internal representation, you might have code like this that the user is not familiar with at all. So that's not really suitable for our situation. So a nice feature of not wanting to expand macros is that we actually don't care about the definition of those macros. And so we don't have to actually look for all those hash defines in all of those header files. Typically, a Linux file might be 1,000 lines long for the .c file and 10,000 lines long if you expand all the header files. So we don't want to, there's about, I don't know how many thousands, maybe let's say 15,000 .c files and about 40,000 files in all. So we don't want to multiply those 15,000 files by 10 and parse all that code. So by default, we only include a very few header files. The only thing header files are really useful for in Coccinelle is finding out the types of things. And often, if you're working on foo.c, then you'll make a special header file called foo.h, and that will have the types that you're somehow most interested in. So that's what we include by default. There's also an option for not including any header files. And then there's some scary options where you actually try to recursively include all the files that you can possibly find, stuff like that. So that's useful for type information. You'll have to go out and buy a larger computer for using it in practice, though. We don't do any kind of program analysis. It goes back to some of the questions. The only thing we do is we do a little bit of type inference. So if the types are available, then we use them. If the types are not available, we don't complain. We just don't use them. So in the example that I showed, we had like expression x, e1, e2. You can also say that, for example, x should be an integer or x should be a structure of a pointer to a structure of a certain type and things like that. Sometimes that's useful for being sure that you're getting the exact right x.y because many structures may have a y field, so you want to be sure you have the right one. But many other times it's just completely useless. And so there's no point to collect information that you're not going to use for anything. So our, sort of our assumption was we did all these kinds of optimizations. It would be good enough. Again, confrontation with the real world. 1 million lines of code is kind of a lot of code. 5 million lines of code, 15 million lines of code, 18 million lines of code is a lot of code. I mentioned as a good thing that we don't actually expand macros. We don't have our header files and everything like that. But on the other hand, as a trade-off, we have a lot of heuristics. We try to parse the things in a bunch of different ways. Actually, if your parsing completely fails, we will have gone over every single function 4 times trying to parse it with more and more different kind of violent heuristics for ignoring things and so on. So this takes a lot of time. Basically, in general, what we would like to do is we would like to avoid parsing as much code as possible. We want to just focus in on the most relevant things. So we have some things that appeared over time. Indexing. So we have a big code base. There's various indexing tools. In the beginning, we used Glimpse. Later on, we used the ID utils. These will go through your document base, your code base, and find all the interesting words. And then we can go through our semantic patch, and we can find all the important words in the semantic patch. So with respect to the rules we saw before, that was not going to do anything if the file doesn't contain at least kmalloc and memset. So then we can remove lots of files that might contain kmalloc or might contain memset, but don't contain both of them or contain neither of them, something like that. And then we'll get a big win on our parsing is slow problem. So here we have some numbers. This is my laptop. It's a ThinkPad. It's kind of a standard developer, Linux kernel developer laptop from a few years ago. So we have two sets of numbers here. One of them is the performance. So these are the semantic patches that are inside the Linux kernel. One is the performance, and one of them is how many files we actually considered. So basically, we analyze the semantic patch, we figure out what are the important words, and then we use our index to only focus on the files that contain those words. So you can see many of the semantic patches, we have almost no files that are being considered. So these are some kind of special purpose things. Maybe there's only 10 files that have to be considered. That goes basically extremely fast. Then we have another set over here. You see, here in some places we jump up to the very maximum thing, which is over 40,000 at that time. These are things that are very generic. So if we're doing something like with null pointer dereferences, there's going to be null. The word null appears everywhere. There's no point to filtering files based on the word null. And this is also, these are things where the developer of the rule thought it would be relevant to header files as well. So that takes more time, or at least there are more files that have to be considered. But you can see that it actually doesn't take terribly much time. I have no idea how much it is. Maybe it's a minute or two or something like that. Then there are a few like pathological cases over here at the end. You can look at this graph. We see we're not actually considering all that many files. It's only down to about 20,000 in this case. So what this shows actually is that the hard thing is not considering more files. The hard thing is the analysis you have to do in some of these files. And when we have those dot, dot, dots, the dot, dot, dot is searching over all control flow paths. So if you have a few ifs, if you have a few loops, then your number of control flow paths will get exponential, and that will take a lot of time. So basically what you can do is you can give Coccinelle a timeout. This is maybe a timeout of 2 minutes or something like that. It's kind of reasonable. If it doesn't figure out anything in 2 minutes, it's probably not going to do anything over time. So this number here, I think it's basically the same amount of time it takes to compile the entire Linux kernel on the same laptop. And so somehow that's considered to be acceptable to Linux kernel developers. Okay, so another question is correctness. We are going over a huge code base. We are making changes all over in the code base. You might hope that your changes are correct. Yeah, maybe. I don't know. Basically, the only thing Coccinelle does in this respect is it checks that the basics is syntactic correctness. We have a little, like a hunk here and a hunk here. It's syntactically correct to remove a complete statement, because statements, you can just have any number of them. It's also syntactically correct to replace one statement by another statement. On the other hand, it's not syntactically correct to just remove an expression. If you just remove 3, then if you had, or most of the time it's not correct. If you have 3 times 4, then you'll end up with times 4. That would not be good. So that's it. Basically, our point of view, there's lots of things you want to express that are perhaps not semantics preserving. So we want to allow you to express those things as well. We basically want to let you express whatever you want. We don't want to spend a lot of time figuring out whether your change is correct or not, so that will improve performance. Basically, we rely on your knowledge of your code base, and our goal is to let you express what you want to express in an easy way. You're supposed to be the expert in what, for example, what kmalloc does. We're not going to figure that out for you. We just want to let you express this kind of change. So I would say confrontation with the real world, mostly the expertise of the developer is good enough to get things okay. Okay, so that doesn't mean that nothing incorrect has ever been done with Coccinelle. Certainly things that are incorrect have been done with Coccinelle, just like things that have been, bad programs have been written using C or Java, all different kinds of languages. But often when the change turns out to be incorrect, it's the developer who didn't really understand what the change was supposed to be, or all of the constraints that had to be taken into account. So it's kind of the developer's problem. So the last one is dissemination. So we have our tool. We made our little research prototype. We thought it was fun to use. We want people to use it. And so the question is, how do you get the thing from your office into basically other people's offices. So our idea was to somehow show by example. In 2007, the first thing we did was to fix some parse errors in Linux kernel code. A nice feature of our approach is that since we are not finding header files, we're not expanding macros, we're not looking at if-defs in any great detail, actually we can be kind of more comprehensive than a standard parser. Like when you compile the kernel, you're compiling it for x86, or you're compiling it for ARM, or something like that. You're compiling it for some specific configuration. And so you may miss a lot of problems that are actually related to some code that's not x86 code. And so we were able to find some just basic parse errors because our parser was looking at everything and not the things that are just specific to a particular configuration. That wasn't really the goal of the project, but it gave a little publicity for the approach. So the first thing we did was this IRQ function evolution. This was another thing, again, where it's a kind of a configuration issue that we were looking at code that no one had been compiling recently, and so they hadn't seen the problem. Basically, some functions had changed their prototype. They had lost an argument, but there were some calls to those functions that still had the extra argument. And so with the rule, then we were able to find this problem in 5 different files in really quite different places in Linux kernel. The third thing we did was this k-malloc memset rule that I showed before. At the time, this change was kind of in progress, and so there were hundreds of opportunities for the change. So we sent one patch. It updated 166 calls in 146 files. So someone thought this was a great idea. I said, cool. But the person who was in charge of actually receiving this patch, evaluating this patch, and getting it integrated into Linux kernel was kind of less happy. Maybe it kind of goes back to what was mentioned in terms of compilers, that we are kind of making more work for someone by doing things automatically. The actual policy of the Linux kernel is that every patch is supposed to be cut up according to which maintainer, like different maintainers work on different things, and you're not supposed to send one patch for 146 files. You're supposed to figure out this file goes to this person, this file goes to this person, this file goes to this person. So now we've made it easy to find these missing evolutions or easy to find these bugs. And at that time, we had actually then we just fall onto another problem, which it's hard to figure out which person is supposed to get which one. So the tools available have kind of evolved since then, and so the problem has kind of gone away. But we had this, you still need the people to review, so it's still work for people. Fortunately, there's lots of these people in the case of Linux kernel, and so the work is often quite highly distributed, and maybe no one complains too much. So in 2008, a non-Coccinelle developer used it. So basically, first we released a binary, then somebody used it, and then afterwards we made it open source. And then more people started using it because I think in general in the open source community, they prefer using tools that are open source as well. So that was kind of got things off, got things started. We also made some more efforts. We had some workshops. Some people from academia came, some people from industry came, mostly just kind of local people, but some fairly active kernel developers attended as well. We made some presentations at various developer conferences. Instead of just, basically in the beginning, we sent things out by email to our target audience, and then afterwards we actually went and visited our target audience from a face-to-face point of view. And then a very nice thing, which is that some kernel developers actually wrote some articles for the Linux Weekly News, which is pretty well read by Linux kernel developers, and so they kind of gave their point of view on whether it was easy to use or useful and things like that. So just to conclude, I'll talk a little bit about the impact. This is a graph about how many lines that have been added and removed in different parts of the Linux kernel. It's a log scale, so in some sense you can't really see anything, but basically, yeah.
Is this lines of code change using patches derived from Coccinelle or
Yes.
code?
Sorry, what's the in total part?
Sorry, I mean, this is lines that Coccinelle has touched as opposed to all the lines that have changed in the Linux kernel regardless.
Yes. Sorry, this are the numbers of removed and added lines that in patches that have used Coccinelle in some way. So as I said, it's a bit hard to see that maybe this is a big difference because we're up higher in the log scale, but the important thing to get from the graph is that it's actually applicable across the entire Linux kernel. Different parts of it has different sizes, but still it's useful in many different situations. This is to try to figure out what people do with it. So I focused it on the maintainers just because it's a smaller number of people and so a smaller number of patches to look at by hand. So people in the beginning, just kind of low usage, some cleanups, some bug fixes, then a bit more cleanups, and then a huge lot of cleanups. And I think that would be kind of the trend in more recent years as well. So the Linux kernel has a number of tools for finding bugs. There may be, some of those tools may be much more sophisticated than Coccinelle. Actually, again, we're not doing any data flow analysis. We don't know about the values of things and so on. Some other tools try to approximate that information in different ways. So they're perhaps better at finding bugs, finding buffer overflows, things that involve calculations. Coccinelle is the only one that lets you do complex changes in your code automatically. So see, these are some of the things that people have done. This is just a few examples. We have a function argument we don't want. So we have to go and find all of the calls to that function and remove that argument. So this affected 11 files in one subsystem. Okay, so maybe it's kind of a restricted amount of code, but still going around to find all those 11 files, it's a bit tiresome. This is a redundant field in a data structure. This time there were 54 fields. This is interrupts. In this case, it's again an issue of we have a function that has an argument that we don't want. But in this case, sometimes we actually did want the argument. So we couldn't just remove the parameter of the function all the time. We had to actually analyze the code of the function and see whether the argument was being used. And if it is still being used, then we have to add some new code to find another way to find that information. So this is something that would be extremely tedious to do by hand. The interrupts is also something that's extremely pervasive in Linux kernel. And so the fact that we are not tied to a particular configuration was very helpful in this case. This is a zero-day build testing service. So this is a continuous integration system that's offered by Intel. Basically, every commit, basically, developers can send their Git trees to this service. And every time they commit something to the tree, the service will run various tests on it, including various tests from Coccinelle. So you can see maybe things got off to a bit of a slow start. But after a while, we can see some of them, the rules that it runs actually offer to change the code directly, and some of them just find issues. So a couple hundred patches each year, and then a bit fewer. But in 2017, over 200 issues were found. A lot of them, some of these actually I validate. Some of them, maybe they're high confidence and they just go to the developer directly. Some of them are lower confidence, and so they come to me. A lot of the ones that I see are related to locks. People forget to unlock their locks. And I would say at least 3/4 of them are real bugs. So again, we're not trying to be like a perfect static analysis tool or even a perfect evolution tool. The idea is to let people express their knowledge about their code and to do something, and then they should look at the results and be sure that everything is as they want it to be. Community, so over time, in the last 10 years, we had 25 contributors, but most of those were just people that we hired and trained and so on. So basically, we have an issue, which is that our audience, our target audience, and the kind of people who develop the kind of code we're writing have just like no intersection whatsoever. But we do have an active mailing list. People ask questions sometimes non-members of the Coccinelle team actually answer those questions, so we have the feeling that people are understanding what's going on. Coccinelle is available for many Linux distributions. It's also available, it's just OCaml code, so it's also available in OPAM now. And it's also used for things other than Linux. So these are things that I know about. There's also Wine. There's also people who ask questions and they don't actually say what software they're working on. So actually, I don't really know. At this time, it was limited to C. There's actually now a Java version, but I don't know if anyone uses the Java version yet, but it's available. So in conclusion, basically, we had some initial design decisions about how we thought a tool like this should behave in order to be useful, in order to be accessible to Linux developers. Those design decisions were refined a bit over time, but we kind of tried to stay within what we were trying to do. We didn't, maybe some people had some issues, they needed some data flow analysis or something like that, but we didn't go in those directions. We just kind of stayed, this is our goal of, we filled it out with more constructs and with the position variables and so on, but we didn't try to stray too far from our original ideas. The tool, something we've really emphasized, the tool should be easy to access, easy to install, easy to use, and robust. So as I mentioned, we use OCaml. It's not the Linux kernel developer's favorite language. But we try to hide the dependence on OCaml. So we would like that you should be able to just download the system, run make, and everything will be OK, at least on the Linux system. But I think it works on Mac and Windows as well. So nearly 8,000 commits in the Linux kernel are based on Coccinelle, so that seems like it's pretty good. And so based on those commits, especially based on the one about interrupts, probably everyone in this room uses some code that we have changed. Okay, maybe even if you're not running Linux on your laptop, you're using Google. Google uses Linux for everything. Facebook, all these companies are using Linux for everything. And so it's everywhere. And yes, phones. I have an iPhone also. And we have a website. The source code is here. It's also available on GitHub. And we have very little documentation. But hopefully it will be easy to use if you try it. So thank you.
Hi, Julia. As a long-time user, I mean, one thing I appreciate, which you rarely get with other systems, is the amount of effort and support you put into it. I mean, someone asked a question on the mailing list, and you're there, you're answering it, and you're very helpful. Mm-hmm. So that must be a lot towards the success of this project. I mean, could you say roughly how much of your time goes into that kind of support activity over a decade of
I don't spend that much time on it. I spend a little bit of time on it. So I work at INRIA. We have it's like a research institution in France, and a very nice thing about INRIA is that they are also willing to hire engineers for you. If you have an interesting project, then you can get someone to help you with the development and maintenance of that project. And so we've benefited from engineers for about the last 8 years or so, different people at different times. And those people have actually helped a lot with the build system, which is something that I do not want to touch ever. But they also have added some new features. Parallelism, for example, somebody took care of that for us. So basically, I work on things that seem very easy to solve and seem very urgent for the person who's asking the question. And the engineers work on maybe the things that seem harder to solve, but not quite so urgent somehow. Or maybe it's just too hard to solve, and so we just can't deal with it in such a short time. So I can't really estimate how much time. It kind of comes and goes. I think I have always found that the things that people ask are the things that I'm going to want maybe 6 months from now or 1 year from now or something like that. And so it's always valuable for us to have feedback from people from the outside. Somebody needs some construct, or like somebody wanted information about comments recently. I don't remember for what purpose. And recently I have had some need. I wanted to understand the comments for something. And so having already implemented that thing was a really great help to my research because I could just go directly. So if you try the tool and you have any concerns, there's some features that you feel are missing, please don't hesitate to, you're not bothering us, you're helping us do something that will be useful in the future. So we'd like to hear from you.
How common is it to use Coccinelle as a refactoring miner? So in the Java communities, there is a tool, refactoring miner, and it basically analyzes a model before and after the changes. So if you rename a method, it will detect it. I think Coccinelle can be used for similar purposes. Do you know whether people have used it for some sort of refactoring miner, mining and classification?
Okay, so what you're asking is, I think what you're asking is about matching patterns in changes that have been performed, whereas Coccinelle is a tool for describing changes that you want to have happen in the future. Okay? However, we've made another tool, since it's quite obvious that these things are very similar to each other. We've made another tool which is called Prequel, and it basically uses a very similar notation, and it lets you match against patches. So the notation is a little bit different because the constraints are a little bit different. When you want to make changes, the added code has to be constructible from the removed code. And when you want to search for changes, then you don't have that constraint anymore. So you can just freely search for all the patches that removed a certain thing or that removed some things and added some things. There's different patterns you might want to do. I've never used it for like mining for well-known refactorings, things like that. I mostly use it for, in practice, I've mostly used it for, like, I've worked with some people, they make a special purpose tool for finding data races or something like that, or finding certain kind of bug. And then I can use the Prequel tool for finding the instances of those bugs that other developers have found before without the tool so that we can validate that our tool is doing better than what was done before or not, and so on. So refactoring, it's kind of a large-scale thing somehow. If you think about it depends on what kind of refactoring you're considering. If you think about refactoring like extract method, that's something that's kind of destructive to the code. And I'm not sure, this is very tied to specific constructs and stuff like that, and so it might not be appropriate. But some other kind of more localized refactorings, it might be helpful to find. Any more questions?
Not a question, just wanted to say thank you for the user interface you gave it by making it resemble patches in a way that it is easy to see how it's evolved. That really clicked for me, so thank you.
Okay, thank you. That was the idea, so.
It worked.
Yeah, okay.
All right,
thank
if
you.
no more questions, thanks Julie again.